So the previous example I gave to you, they all have two eigenvectors for the two-dimensional matrix. That's a perfect situation. But let's observe the third transformation. We call it sharing transformation. And in the beginning, you get this rectangle. And then if you put some force, squash this rectangle in that horizontal direction, it gets the sharing transformation. The new shape will be a squashed parallelogram. That's called the sharing transformation. In this transformation, you can clearly see this red vector u, which is horizontal, 1, 0, that's not a change. You can multiply b to the u, do quick calculation, and then 1 times 1 is still 1, and the 2 times 0 is 0, and then 0 times 1, 1 times 0 is 0. Of course, did not change because you're only sharing on the top. But can you find another one? Not parallel to this horizontal direction. You can try. Let's find any other vector. If it's like this, when you do the sharing, it will go move like that. Can you see it? If we give another vector, you're doing the sharing, you add another vector, it will move. They all change direction. So the conclusion is, in this transformation, you only can find one eigenvector. If you find more, they're all horizontal, parallel to this direction. By the definition I gave in last lesson, we call this matrix as defective matrix, right? Let's do a proof. They only have one eigenvector. The proof is nothing more than a little calculation. You let this b minus lambda I, that's what we call the characteristic equation, equal 0. Then you have 1 minus lambda, 2, 0, 1 minus lambda equals 0. Then you got a repeating solution, lambda 1 equal lambda 2 equal 1. Oh, you only got one eigenvalue repeating. Can you find two eigenvectors? The answer is no. They're not independent. Let me call the eigenvector as v equals a and b. You want this b minus lambda I, by definition, times v equals 0. And then put a 1 there is 0, 2, 0, 0, times a and b equals 0. If you have done your homework, you know this is how we calculate the eigenvectors. And then you get that the 2b equals 0. That's the only equation. Then b equals 0. What about a? Free. You get the 1 freedom because the rank equal 1. See, the rank equal 1. And then 1 freedom. What are you going to say? The a equal 1. How about the equal 2, equal 3? They're all good, but no difference. That's the only eigenvector. Since you have the 2D matrix, you only got one eigenvector. That we call it defective. Well, let's look at other transformation. A couple of lessons before, we look at the rotation matrix. In this case, to make things simple, I only choose theta equal pi over 4, and then put into this rotation matrix, cosine pi over 4, we know is the square root of 2 over 2. Sine pi over 4 is also square root of 2 over 2. The negative sign is negative square root of 2 over 2. Then I put it here, it's going to be square root of 2 over 2, negative square root of 2 over 2, the same, the same. That's the A. So what is the eigenvalue? Try to look at the characteristic equation. A minus lambda, I'll call it R, I equals 0. Then we get this minus R. Everything copy, but on the major diagonal, make a minus R. Then you get this. Square, negative, negative, make a positive, plus. That's interesting, right? To complete a square need to equal 0. The only solution you can get is imaginary. You don't have a real solution. If you don't have a real solution, you have this imaginary solution plus minus the square root of 2i. Then you really cannot find any vector whose direction does not change. Let's observe. Then you will find it, say, of course, it won't change. Everything changed. If you have any vector here, what this operation do is going to be rotate 45 degrees to here. If every vector rotate 45 degrees, of course it changes the direction. Direction is represented by the angle, right? If you change 45 degrees, of course changed. So in this rotation matrix, you cannot find any single vector does not change direction. So does not have real eigenvectors. That is what we call it self-joint, by the way, related with a lot of Nobel Prizes, if you have a real one, but we don't in this case. Well, I'll give you as an exercise, want you to look the theta equal pi. That will be interesting. If theta equal pi, that's exceptional. And you can, to try the exercise and the answer, do you have a real eigenvector? The answer is yes for that. So rotation matrix, unless it's a special angle, you don't have real eigenvalue.